All right, so now we're ready to do examples and apply what we've learned about taking derivatives of parametric curves. So curves that are written with parametric equations, all right? That's what a parametric curve is. All right, so now we're ready to apply those derivative rules that we've learned. So question A is, okay, I've got a curve and here's my two parametric equations. So A says show the curve has two tangents at the point 3, 0 and find their equations. All right, so I need to have two tangents at the point 3, 0 and find their equations. So how can we figure out their equations and why there are two problems? All right, so the first thing you need to do is we need to put in the point 3, 0. So 3 is our x-coordinate, so that means 3 equals t squared. So t is going to be the square root. So that's positive and negative square root of 3. All right, so our x-coordinate, there's 2 points there, 2 values. All right, but we also need to do the y-coordinate. So our y value is 0. So now we need to put a y here, or put the 0 in for y. So 0 equals t cubed minus 3t. Because what has to happen here, the t value has to be the same number to give us the points simultaneously, 3, 0. So I have to have the same t value that gives me a 3 for x, that the same t value has to give me a 0 for the y value. So that's why I'm setting both of them. The x is 3 and the y is 0, and I'm solving these equations, and I got to find the common answers that they have the same. All right, so for this problem, I'm going to factor out a t, and that gives me t squared minus 3. And so now t equals 0, that's this term here, or t squared minus 3 equals 0, which means t squared equals 3. So taking the square root, t equals positive and negative square root of 3. So this part of the problem has 3 answers given so that I can get a y value of 0. So that happens 3 times. Over here, it happens twice where I get an x value of 3. Now, in order to have this point, I have to have the 3 and the 0 occur at the exact same parameter value. So since this first one doesn't have a 0, I can't include that one because at 0, obviously, x is going to be 0. It's not going to be 3. So that doesn't work for the point 3, 0. So our 2 points, our 2 values are going to be t is positive and negative radical 3. So that was the first part of the equation. Show that the curve has 2 tangents at the point 3, 0. So I have 2 of them. I have one tangent line when t is positive radical 3, and I have another tangent line when t is negative radical 3. So now I've got to find their equations. So in order to find their equations, I need to find a point, which I already have that. The point is 3, 0. And then I need my slope. So all I need to write the equations now is slope. So that's the last thing I got to find. So how do we find the slope? Well, that's your dy dx. And we know to do that, we need dy dt divided by dx dt. All right, so I need the derivative of the y. So the derivative of my y parametric equation is going to be 3t squared minus 3. So 3t squared minus 3. And then divided by the derivative of the x parametric equation. So the derivative of that is going to be 2t. So there is my derivative. So now all I have to do is find the slope for each point. All right. So when t is positive radical 3, what is this going to equal? Well, that's going to be 3 times radical 3 squared minus 3 over 2 radical 3. So that's going to give me square root of 3 is 3. That squared is 3 times 3 is 9 minus 3 is 6 divided by 2 radical 3. So then when I reduce that, we're getting 3 over radical 3. All right. So that means, and then if I rationalize it, right, you can rationalize that, or you can leave it that way. It just depends on which form you want to have it. If we rationalize it, it would be radical 3 over radical 3, which gives me 3 radical 3 over 3, which is just radical 3. So you could either leave it in the form 3 over radical 3, or you could rationalize it, and that turns out to be radical 3. So that means that's one of my slopes, okay? Now, the other slope is when t is the negative radical 3. So now I need to plug negative radical 3 in here. So that'd be 3 times negative radical 3 squared minus 3 over 2 times negative radical 3. So again, that's going to give me 6 over negative 2 radical 3, which is going to be the same answer, just negative. So that's going to be a negative radical 3. So this is slope number 1. This is slope number 2. So what are my two equations? So my point is 3, 0. And my two slopes, one of my slopes is radical 3. The other slope is negative radical 3. And that's kind of quinky-dinky that it turned out to be the same as your t-values. Don't think that. If that was it, then I would have stopped there. It's not. All right, it just turned out, the math turned out that way. So one of my equations is y minus 0 equals radical 3 x minus 3. And the other one is y minus 0 equals negative radical 3 x minus 3. Just putting my point in my two slopes. So here's my two answers. All right. So I had to find the t-value that gives me, since we're doing parametric equations, I had to find the t-value that gave me the point 3, 0. So I had to do x was 3, I had to do y was 0, and they have to have the same common parameter value. So that's why we threw out the 0, because the x one, the x coordinate one, did not have a 0. When t is 0, x is going to be 0. So that's not going to give me the point 3, 0. So they have to have the same common parameter value in order for that parameter value to work to get us the 0.30. Then to find the tangent line, I needed my slope. So that was using the slope, using parametric equations. And so I calculated my slope. And then we're using the t value. Since this is in terms of t, I just had to put both of my t values into my derivative to find the slope of the tangent line. And then we wrote the tangent lines. So that's just recapping what it did. All right, number 2. It's the same parametric equations. All right, I did not change that. I'm just going to ask a different question. Find the points on the curve where the tangent is horizontal or vertical. Find the points on the curve where the tangent is horizontal or vertical. All right, now think about what our derivative was. Now we found our derivative already. So when we did dy dt over dx dt, this is the same problem. It's 3t squared minus 3 over 2t. So there's our derivative, okay? So we learned this in AB, okay, about horizontal and vertical tangent lines, all right? If you have a horizontal tangent line, that means that your top is, the numerator is 0. If you have a vertical tangent line, then that means the denominator is 0. Now, something that is different in this particular set of problems, because it's parametric equations, and your t value is in both the top and the bottom, you have to make sure, like, if for horizontal, and this is on that sheet, okay? If you look on your sheet that I gave you about parametric equations, it's written on there that to do horizontal, the dy dt, which is your numerator, the dy dt equals 0, but the dx dt cannot be 0, because I can't have 0 over 0. So I can't have the same t value that'll give me a 0 in the denominator, because you don't want to have 0 over 0. You want 0 over some other number so that you get the answer 0 and have a horizontal tangent line. So on that sheet, the parametric equation sheet I have, is at the bottom. It says a horizontal tangent. It says dy dt has to equal 0, but dx dt cannot be 0. All right. So I'm just going to solve this. I'm going to say dy dt, so 3t squared minus 3 has to equal 0, but my denominator 2t cannot be 0. All right, so I'm just going to solve these. So 3t squared equals 3, so t squared is 1, so t is positive and negative 1. And then the other one is pretty easy. Divide by 2, t can't be 0. And that's perfect because if I've got t is positive and negative 1, that's not 0. So I don't have to cross out an answer. These are my two answers. I just can't have whatever answer comes up here. I can't have it in this group. So if this had been t can't equal 1, then my answer would only be negative 1. So it just depends. You just don't want to have the same. All right. So that means my answers are t is 1, t equals 1, and t equals negative 1. Okay, so it says find the points. Well, so then how do you find your points? Well, t is 1, you just put a 1 in up here in these equations. So when t is 1, the x-coordinate's 1. When t is 1, the y-coordinate's negative 2. Just putting a 1 in up here. All right. When t is negative 1, if I put a negative 1 in here, my x is also 1. And when I put a negative 1 in here, my y-coordinate is going to be negative 1 plus 3, which will be positive 2. Now, so that's horizontal. Horizontal, yeah, I spelled it right. All right, now we want to do vertical. So with vertical, you've got the reverse, okay? So if I have a vertical tangent line, I want 2t to equal 0. Well, let me write it the other way first. It's on the bottom of your sheet. You want dx dt to equal 0, but you want dy dt to not equal 0. Again, we don't want to have 0 over 0. We just want a number divided by 0. So our numerator can't be 0 or we got a problem. So, of course, these are going to be the same answers over here. Your 2t has to equal 0, so that means t is going to equal 0. But our 3t squared minus 3 can't be 0. So our numerator can't be 0. And we know that means t cannot be 1 or negative 1. Okay? And nothing conflicts, so this is your answer. Okay? So we want it to be 0. That's not over here in the list of what it can't be, so we're good. T 0. So with t equals 0, what's the point where we have a vertical tangent line? So I put a 0 in for my t's. So I get x is 0. I put a 0 in for my t's here, and I also get 0. So at the origin, we have a vertical tangent line. Okay? So again, those are at the bottom of your sheet. So to do horizontal, the numerator, your dy dt, has to equal 0, but your denominator, dx dt, cannot be 0. To do vertical, you want your denominator, dx dt, to equal 0, but your numerator, dy dt, cannot be 0. So you just have to figure out, of course, I didn't have to do the algebra twice, obviously. You just want to make sure that none of the answers overlap or you got an issue. So that's part B. Part C. So part C says determine where the curve is concave up or concave down. All right, so to do concave up and concave down, you have to do your second derivative. Now remember, these are the same functions. I have not changed the functions. They're exactly the same. So if you remember our first derivative, dy dx, which is the dy dt over the dx dt. So there's our first derivative. So then we want to find the second derivative. All right, so our second derivative would be the derivative dx of dy dt. I'll write it just like I did before, the dy dx, which is going to equal d dt of dy dx divided by dx dt. That's your little rule. So what you do is you take the derivative of your first derivative in terms of t's, and then you divide by dx dt again. All right? And dx dt is 2t. I'm going to put that in there. So I just need the derivative of this in terms of t's. Now, what will make this derivative a little easier is if I spread this up, instead of doing a hody-high, if I take this and split it into two fractions, if I write 3t squared over 2t minus 3 over 2t, and then rewrite this as 3/2 t minus 3/2, and then make this a t to the -1 by moving that t in the denominator upstairs. Then taking the derivative of this will be a whole lot easier. All right, so the derivative of this then will be 3/2, because the derivative of 3/2 t is just 3/2. And then the derivative of this part, I multiply the -1 times the front, which will make plus 3/2. And then I drop a degree, so that'll be t to the -2. All right, so again, I can split this up again to make my math a little easier, because I've got this denominator right here. I'll split this up into 3/2 over 2t. So the algebra, calculus, the algebra is what gets you over 2t. So if I simplify this, this is going to be 3 over 4t, because think about what we thought we did earlier. If I put a 1 under this, it's outers over inners. So that's going to be 3 over 4t. Then for this one, 3/2 divided by 2 again is 3/4 again. And I can just move this t to the -2 to the denominator, so that's going to make a t cubed on the bottom. All right. Now, if I want to put this back together, I need a common denominator. So my common denominator is going to be a 4t cubed. So that means I need to multiply this guy times t squared. So this will be a 3t squared. If I multiply by t squared, t squared. So then I've got 4t cubed in the bottom. So that's 3t squared plus 3. So that's just making that derivative look a little nice. All right. So why did I do all that? So that gives me that my second derivative, all right, that's using just the second derivative term, 3t squared plus 3 over 4t cubed. Here's my second derivative. So we want to know where the curve is concave up and where it's concave down. All right, so remember your second derivative tells you about the concavity. So if you're concave up, so concave up is where your second derivative is greater than 0. And if you're concave down, that's where your second derivative is less than 0. All right, so I need to think about what t value is going to make that expression exactly what I'm saying here. All right, so let's take a look at our numerator. It says 3t squared plus 3. Well, since this is a t squared, that's always positive. So my numerator is always going to be positive no matter what I put in here for t, because I'm squaring it. So my denominator is what's going to determine the sign of the second derivative. So if I need my second derivative to be greater than 0, if I need it to be positive, that means I need to have t greater than 0. Because if t is positive, then this whole expression is going to be positive. If I want my second derivative to be less than 0, what's going to make this expression negative is if t is a negative number. So this is my answer. So we're concave up when t is greater than 0, and we're concave down when t is less than 0. And that's the answer to the question. So this is my answer. All right. Now, simplifying the algebra to this is what makes it easier to determine. If I'd have left it up here in this form, that would have been harder to do. Even leaving it as two separate fractions makes it harder to do. So if you get it as one fraction, then you're able to determine what's going to make it positive, what's going to make it negative. So that's why I did that little bit of algebra. All right. So the next problem, these are all example 1 because they all are dealing with the exact same parametric equations. Okay. So now let's do what we did in section 1 and let's sketch this. Okay. So let's sketch it. So I'm just going to go through this real fast because I know you know how to do it. So we got our t, our x, and our y. So I would just pick some numbers here, -2, -1, 0, 1, 2, and then I'm also going to do radical 3 and negative radical 3 just because those were answers to the problems on the previous slides. Those answers, plugging them into these parametric equations, I'm just going to copy it down real fast. These are 4 and -2, 1 and 2, 0, 0, 1, -2, 4, 2, 3, 0, and 3, 0, because that's what that previous problem was, I believe, in A. Yeah, in A, we had the 0.30. So now if I sketch this thing, you're just sketching these points on here. So I've got 1, 2, 3, 4. So I start at 4, -2. So I start down here, and then I go to, these aren't in order actually. The -3, this 30 would be next because my numbers are not in order. Then the -1 would be next. So then 1, 2 would be next. So it would come up here next. And then the 0.00 would be next. So then it would come down here like this. Then I would go to the point, then we would go to 1, -2, which would be here. So then it would come down here. Then the next point I would go to would be the positive radical 3 one, which would be the 30 again. So that would come up to here again. And then my last point would be the 4, 2. So then the 4, 2, and so it looks like a little ribbon there, sideways ribbon. Okay, so now there's what the picture looks like. So we start down here and we roll around. Of course, this can keep going this way and this keeps going this way, depending on, getting T going positive, negative. So it looks like this little twirly. Okay, now let's take what we learned, what we found out in the last few problems. All right. So if we go back to A, in A, it said show that there are 2 tangents at the point 30 and find their equations. So we did. We found 2 equations. One of them had a positive slope, one had a negative slope. So if I go back to our picture we have over here, at the point 30, we have a tangent line, because when we come up here this way, this has a tangent line this way, and then when we twirl around and come back around this way, it has a tangent line going that way. So it has a negative slope tangent line and it has a positive slope tangent line. All right, so that's those 2. All right, then on part B, we were looking for horizontal and vertical tangent lines. So at the point 1, -2 and 1, 2, we have horizontal, and at the point at the origin, we have a vertical tangent line. So let's look at that. So at the point 1, 2, we have a horizontal. At the point 1, -2, we have a horizontal. And at the origin, we have a vertical tangent line. All right, so everything we figured out has happened, all right, using our calculus. So then on part C, it said determine where we're concave up and concave down. So we said when T is greater than 0, it's concave up. And when T is less than 0, we're concave down. So let's go back to this picture. So if I had filled in my T's here, this was -2, negative radical 3, this is -1, and then here's 0. So when our T was less than 0, this is concave down. Then when T was 1, radical 3, and 2, that's when T is greater than 0, it's concave up. So everything that we did on those previous slides, when you graph it, you see that all of those things happened. Isn't that cool? Voila, woo woo, so exciting. I love math. All right, so now let's get on to I just wanted to show all those different things. All right, so now let's get into, this is a cycloid. It's defined by parametric equations. Here's our x and here's our y. It says find the tangent line at the point where theta is pi over 3. Okay, so the first thing it's nice to do on this is it's nice to go ahead and distribute this. So x is going to be r theta minus r sine. And over here, y is going to be r minus r cosine. So all I did was just distribute across the parentheses. Okay? So now, to find your tangent line, we need our derivatives. So we need our dy dx, which we know is dy dt divided by dx dt. Okay? So I need the derivative of the y one divided by the derivative of the x one. Just don't do the common mistake and do the x first. So we always do the y first. So the derivative of this. Now, in this problem, r is a number. So the derivative of r is going to be 0 because r is just a number. It's not a variable. The theta is our variable. So the derivative of r is 0. And then this is a coefficient, so negative r. And then the derivative of cosine is negative sine. So that's going to end up making this positive sine theta. Then we're going to divide it by the derivative of the x part of the parametric equation. Remember, r is a number, so this is like having 3 theta, where thetas are variables. So the derivative of 3 theta would be the 3. So the derivative of r theta is going to be r minus, and again, this r is just a coefficient, and the derivative of sine theta is going to be cosine. So there's our derivative, and you'll notice everybody has an r in it, so you can factor out your r. This is r sine theta. If we factor out an r out of this bottom one, we're going to have 1 minus cosine. So the r's can cancel. So the actual derivative is just sine theta divided by 1 minus cosine theta. So there's our derivative. All right. So it says find the tangent where theta is pi over 3. So all we got to do is plug in. Go plug in theta equals pi over 3. All right. That's all I got to do. So I'm just taking the derivative and plugging in theta is pi over 3. So I'm going to do the sine pi over 3, 1 minus the cosine of pi over 3. All right. So the sine of pi over 3 is radical 3 over 2. Think about just on the unit circle. And then 1 minus the cosine of pi over 3 is 1/2. So we're going to get radical 3 over 2 over 1/2. 2's cancel. So the answer is radical 3. So that's our theta. So now that is your slope where theta is pi over 3. Now remember, theta is our t. It's like our counter, our t. So we found the slope. This is the slope of our tangent line. What we need is our point. So now to find your point, you have to go up here to your x and y coordinates, and you have to plug in pi over 3 in for theta to find your x and y coordinates for the problem. So our x coordinate is going to be r times the theta, which is pi over 3, minus r times sine of pi over 3. So we're going to get r pi over 3 minus r, and the sine of pi over 3 is radical 3 over 2 again. Okay? And you can just leave it like that, or you can factor out the r if you want to. It doesn't matter. Okay? Now we need our y coordinate. Our y value is putting in pi over 3 for the theta. So that's going to be r minus r cosine pi over 3. So that's going to be r minus r, and the cosine of pi over 3 is 1/2. So again, if you want to take out the r, you can factor out the r to be 1 minus 1/2, which means our answer is 1/2 r, or r over 2, however you want to write it. All right, so this is your x coordinate, this is your y coordinate, and here's your slope. So now you can write the equation. I know it's kind of funky looking, but you can write the equation for tangent line down. So our tangent line is going to be y minus our y coordinate, which is r over 2, equals our slope, which is radical 3, then x minus our x coordinate, which is, if it'll stop twirling, r pi over 3 minus radical 3 over 2, close parentheses. So there's my equation. That's my answer. Now, this is not hard. It's just multi-stepped. So you had to find your derivative. You had to find what the derivative equaled at pi over 3, which gives you your slope. Then you had to also go and get your parametric equations and put in pi over 3 to figure out your x and y coordinate of the point on the curve that you're looking at. Then you can write the equation of your tangent line by using the point and the slope. All right? So you just have to remember we're doing parametric equations. So you had to find your point for x and y. So that's an extra step we've never done before because we were not doing parametric equations earlier, right, when we learned about this stuff. All right, so this is the same problem, same set of parametric equations. So I just wanted to do some more about at what point do we have a tangent that's horizontal. So if you remember, I'll go ahead and just write down, we won't calculate it again. Our derivative was sine over 1 minus cosine. That was our derivative that we found on the previous slide right here, sine over 1 minus cosine. So that was our derivative because these are the same parametric equations. So we want to know where is our tangent horizontal. So if you look at the bottom of your sheet, to have a horizontal tangent line, that means your numerator, which is dy dt, has to equal 0, but your dx dt cannot equal 0, all right? So our numerator, in order to have a horizontal tangent line, our numerator needs to equal 0. So that means sine has to equal 0. But our denominator cannot be 0. So 1 minus cosine theta cannot be 0. Okay? So where is sine equal to 0? So you think on the unit circle, where is sine 0? Well, that's going to be at the points 0, pi, and 2 pi, okay? Then over here, we solve for cosine here. So I'm going to move the cosine over to that side. That means cosine cannot equal 1. So where on the unit circle does cosine equal 1? Because we can't have theta be that value. Cosine is 1 at 0 and 2 pi. So that means theta can't be 0 and 2 pi. So over here on these solutions here, it can't be the 0 and the 2 pi, so it has to be the pi. All right? So pi will give us a 0 on the top, but it won't give us a 0 in the denominator. The other two will give us 0 on the top and the bottom, and that's undefined, so that's not going to be a horizontal tangent line. So pi is the only one that will give us 0 in the numerator and give us something else in the denominator. All right, so when theta is equal to pi, we want to know what the point is, so all we got to do is plug it into these coordinates. So our x coordinate is putting in a pi for our theta, so that's going to be r times pi minus sine of pi. All righty, and the sine of pi is 0, so that's just going to give us r pi. And then to find our y coordinate, we're going to put pi in up here again, so r1 minus cosine of pi. And the cosine of pi is -1, so this is going to make 1 minus -1, so that's going to be 1 plus 1, so that's going to be 2r. So that means the answer for the point is the x-coordinate is r times pi, and our y-coordinate is 2r. So that means if they gave us any cycloid with whatever value of, just a second.
011, Miss Dills, 2011.
So if they gave me any cycloid with any value of r here in these expressions, if r was say 3, then this answer down here would be 3 pi 6. If they gave me a cycloid whose r value was 5, then that means down here this would be 5 pi and 10. So this is a generic answer for whatever radius or r value that the cycloid has, okay? All right, very last problem. So now we're just going to refresh and do the vertical part, okay? So doing the vertical. So again, our dy dx, our derivative from last time, remember, was sine over 1 minus cosine. So to have a vertical tangent, that means the denominator, dx dt, has to equal 0. But our numerator, dy dt, cannot be 0. So that means 1 minus cosine has to equal 0, but sine cannot equal 0. And as we did a few minutes ago on this problem, the theta here for this problem was 0 and 2 pi. Over here, the theta was 0, pi, and 2 pi. So that means it can't be either one of them. Because this can't be 0, pi, and 2 pi, it can't be these guys over here. Which technically just means that our test fails us. So what we have to do is do a limit test, because this particular test is just doing 0 on top. So we got to figure out, does it approach 0 or not? So we're going to do what's called a limit test. So we're going to do a limit and let theta go to 0, because all of these guys failed out. They bailed out on us. So we're going to take our derivative and we're going to figure out, does this ever approach 0? All right. As theta approaches 0, which is one of our numbers here. So we're going to test and see if 0, because these are our two possibilities that get canceled out and we get nothing. So we're going to test to see if we've got a possibility at 0. So I'm going to do let theta approach 0 and see if something's happening here. All right. Because we end up with 0 over 0 here and we get 0. So we're going to do L'Hopital's rule. What we're doing. So sine of 0, 0, cosine of 0 is 1, so that gives me 0 over 0. So I'm going to do L'Hopital's rule. So now I'm going to do the limit, and I'm going to do L'Hopital's rule. The derivative of sine is cosine. Derivative of 1 is 0. Derivative of negative cosine is going to be sine. So now when you put a 0 in here, this is going to be 1 over 0. So this answer goes to infinity. So that means there actually is a vertical tangent line here. Okay. Then the other one that we're going to do, and you don't have to do this very often. Now I'm going to do 2 pi. Because these are my only two options and they both canceled out. So what we're doing is checking to see if there's actually a possibility. So now I'm going to do the same thing. Sine over 1 minus cosine. So now I'm going to do the same thing. Go to 2 pi. Going to 2 pi gives you the same thing, 0 over 0. So I'm going to do the limit, do L'Hopital's rule again. Except we're going to 2 pi. So now I'm going to do same thing. L'Hopital's rule. So the derivative of sine is cosine. The derivative of 1 minus cosine, derivative of 1 is 0. Derivative of negative cosine is positive sine. And so then when you do 2 pi in here, at 2 pi, the cosine's 1. At 2 pi, the sine is 0. So you have 1 over 0. So that also goes to infinity. So there's also a vertical tangent line there. All right. So we actually have a vertical tangent line at those 2 points. All right. So now, where theta equals 0, we now need to find our x-coordinates. So where theta is 0, you go up here and you put in your x-coordinates. So let's see, that's 0. Sine is 0, 0, so that means x is 0. X equals 0. And then for y, you come up here for 2 pi, and you put a 2 pi in here. So cosine of 2 pi is 1. 1 minus 1 is 0. So that gives us the point 0, 0. So now let's put in theta equals, because you're going to get a different answer, theta is 2 pi. So now let's do my x-coordinate for that. So if I go up here and put a 2 pi in, the sine of 2 pi is 0. But I'm going to put a 2 pi right here, so my answer is going to be 2 pi times r. So that's going to be 2 pi times r. And my y-coordinate, if I go up here, my y-coordinate, I'm putting in a 2 pi here. The cosine of 2 pi is 1. 1 minus 1 is 0, so that's going to give me a 0 again. So that means that point is going to be 2 pi r, comma 0. So there actually are 2 vertical tangent lines because these guys, it said it couldn't be 0 and 2 pi, but that was my only 2 options over here. So I did a limit test to see if it's approaching a vertical line or not. And so this happens every now and then. You don't have to do it very often. Just when it wipes out everything, you just want to test them. If it wipes out all your answers, you test them just to make sure. All right. And I know that was weird. We'll do some more of that when we're doing our live Zoom time. So you've got a target assessment and you got some practice problems. So on your practice problems, you've got page 651, numbers 1 to 21 odd. And then I also added in there problem 22. All right, so go work out using the derivatives, both the first derivative and the second derivative of our parametric equations.